Okay, so my Zoom is, you get an account from UH that lets you do over 40 students or over 100 students in over 40 minutes, which obviously our class is over. So I switched that over from Michelle was starting them um, for me, and that obviously isn't good in case we have a problem or something. So now I control it. And then I didn't put in, I mean, you guys already all know this, but I didn't put in a password. I don't think there's anybody that's not in the class that's really wants to come in and hang out for our lectures and see this anyway. So um, we left off here and go have it go full screen. With polyatomic ions, and I put a sheet that's on Laulima, and I'll pull it up here too as well, that has the ones that you want to know and that you'll see the whole year of chemistry. And anybody that's bio, you'll also see in OChem as well. Now, I haven't taught this class 161 online yet. So obviously, these online tests are a little bit different. It's basically open book, open note, because I can't be there to see what you have taped up on your wall. So the tests tend to be a little bit harder and be more math things with made up chemicals and stuff, so that you can't Google them. That's the way you kind of have to do these things now for these online classes. So the sheet that I send out, and then I'll pull up and show you, I say you have to memorize it, but if you have it just taped on the wall, how would I know the difference anyway? So, but the better you know things, the easier the exam is going to go. Right. So it's supposed to be, tests are really supposed to be a test of the knowledge of what you know and have learned, not who can look up and Google and find a way to find the answer. Right. So the better you know the things, the less time you spend looking for the answer, and the more time just solving the problem, obviously, the better. And the test is I'm gonna try to reduce that. Anyway, polyatomic ions are like they sound. So poly means many, atomic, right, is atom, and then ion is a species with charge. All right, so for these, you need to know the name and the charge. They don't change, and they're just like our compounds, our ionic compounds we talked about before. So this is sort of the full version that's in most normal books. There's quite a bit of these to memorize. So this first one, acetate, is really more of an organic chemistry one. I don't use this one too much. I don't think it's, that you need to know it. Then these chromate ones, they were used quite often, and in Chem 162 in some of the labs, but the cost waste-wise to get rid of these is quite high, and so heavy metals are expensive to get rid of. The other things can go down the sink. They're just bleach and baking soda and like cleaning solutions, ammonium hydroxide and whatnot. So the ones in black are the ones that are more important. These chloride ones, they get used in paper production and explosives and stuff. So they're relevant, but really kind of only if you're in those two fields. All right, so this just walks you through those naming patterns that are up there. So I don't use these chlorate and bromate ones too often. They're not as, the chlorate, everything with chlorine is more common than bromine. Bromine's more rare than chlorine, and it's much more expensive, but they follow this, they're in the same group, so they follow the same pattern. So with these polyatomic ions, you kind of just need to memorize the one ion and it's a charge, obviously. Then if there's a hydrogen in front of it, you just add hydrogen to the name. So for example, carbonate is the one that's in carbonated drinks, right? And if it's hydrogen carbonate, then the charge goes down by 1 because it has a +1 hydrogen there. So here's this general trend, and notice all of these are a lot of these polyatomic ions are oxy ions. And what I mean by that is you notice it's all whatever group they're in. This one has it nicely oriented by the periodic table. And then oxygen atoms have attached to that one, to that central atom. The borate you'll see in OChem, we won't use that too much. So it's really the carbon, nitrogen, phosphorus, and sulfur ones. Silicone, arsenic, these ones in purple, they're more expensive. They don't get used as much. Then again, the chlorine one is more in like bleach and paper mill stuff. So you won't see it too often. Okay, so once you know the root polyatomic ion, then it has this 8. That's the normal version. If you add an oxygen to it, you put a per in front of it. So for example, chlorate becomes perchlorate, right? Same exact species, but one more oxygen. Same, but in the opposite direction. If there's one less oxygen, it's ite, ite instead of 8. So chlorate becomes chlorite. If it has 2 less oxygens, then it becomes hypo. And you keep the ite, so right, it was chlorate, then chlorite, and with 2 less oxygens, it's hypochlorite. This trend you see through most of these, but I'm not going to use the chlorine ones on a test. Again, paper mill and explosives, so it doesn't get a lot of use. And there won't be, I don't think I'll even put a naming on the test because you could just Google search the formula. So we're just going through where it comes from. And because we're going to balance equations, that'll obviously be on the first exam. We're just going through where these come from. So now, once you know your polyatomic ions or what it is, then it's just the same as before, right? The sulfate SO4 2- is our polyatomic ion. Sodium is a +1, so we need 2 of them, right? The polyatomic ions are all 1 unit. So when you need more of the polyatomic ions, you need a parentheses around them. And you don't need to indicate the number, right? The charges are fixed for these two. So it's just sodium sulfate. And here's a good example where you need parentheses around it. So what this is saying is we have nitrite, but we have 3 of them, right? So the NO3 is a fragment that stays together. If you just write the 3 without the parentheses, then it looks like NO and 33 oxygens. Okay, so the charge on the polyatomic ion is fixed. It's a -1, and we got 3 of them. So that must mean the species is neutral. So that must mean the iron's a +3. We show that with the Roman numeral. So iron 3 nitrate. Okay, we don't need to spend too much time on it. Sorry, the animation there, because you can just Google these things during an exam. So I might put 1 on there, which is darn near a freebie. But if it was an in-person class, then you'd have to have these things known and memorized, etc. But it's an online test. So this ammonium is NH4+ is good to note because you'll see and use that a lot in acid-base chemistry in 162. And I think everybody's major, almost all of them you have to take 162. There's a few obscure majors that don't have to take, that just do 161. Okay, then, so we don't need to spend a lot of time, but this procedure is just the same, right? That crisscross pattern worked good, but here you can see the charges are the same. And then they did this where you just reduce it, right? If there's 3 of each, it's the same as just 1 of each. Or you can just see that the charges are equal and it's neutral. Again, another example, but I'm not going to, maybe one of these naming things on the test, and I'm not even sure about that. And especially if you just have this sheet that I've mentioned taped up, then really you'll just be using the periodic table with the sheet and matching them, and you'll just be treating these polyatomic ions just like a monoatomic ion that we covered before. All right, this is a good spot. So let me change the share. And so here, this is the sheet that I make up when I do 161, and you can see it's a bit more abbreviated than what's in the slides. And I don't have any of the chlorate and bromate ones in here, again, unless those are just basically used for bleach and paper and some explosions and propulsion and whatnot. And then these hydroxide, you'll see quite a bit in ammonium, and that's acid-base chemistry, which we haven't really covered. You'll go into the math behind it in Chem 162, right? And then this is the important trend where one less oxygen. Note that the charges are all the same, right? -1, -1, -3, -3, -2. And then for carbonate, there's no such thing as carbonite, right? CO2, and that's what we breathe out. It's a gas. Then the same thing here for the hydrogens, but again, this is more important for Chem 162 when you do acids and bases, but this is the point, the right place to introduce it with naming and whatnot. Okay, so what this is trying to show you is that some things, some solids, some chemicals are very water loving, but the waters don't actually make a covalent, or obviously I'm not ionic because water isn't ionic, but they don't make a formal bond. So they get what's called hydrates. And the way you go from a hydrate to anhydrous, right, just means hydro means water. So without water, you just put these things in the oven for a day or so, and the water slowly is driven off. And then the number of waters that are there. Hemi is rare, but means half. And then these are just these prefixes that I think most of you have seen before. 1, 2, 3. You've played Tetris. You've heard of a tricycle, right? The pentagon, hexagons, the honeycomb, and on soccer balls, etc. So again, I'll only put one naming thing on the test, and so we don't need to spend too much time on naming. But the more familiar you are with these things, the easier it is later on in the semester and in Chem 162 that you know what chemical they're talking about, and you don't have to go look it up. And so I think it does one here. So what's the formula for magnesium sulfite heptahydrate, right? Hepta 7. Magnesium's Mg, go to the periodic table. So here's where if you have sulfate memorized, you don't have to go look it up. But again, on a test, you could have the sheet that I give you taped up on the wall. So, the exam is supposed to be what you know, not what you can just look up. So most of our problems are going to be some kind of math, not this simple. Then this one's doing nickel chloride. So the chlorines have a fixed charge of -1. There's 2 of them. The thing is neutral, so it must be nickel 2. And then hexa means 6, so 6 waters. And they put this little dot here to show you that it's not bound to it, that it's one of these hydrate things. Okay, naming binary molecules. What that means, bi means 2, like bicycle. It means if you have 2 atoms that come together, now they're nonmetals. So there's not a big list of nonmetals. And it's handy to always have the periodic table out. I'd say, if you, obviously if you're in your car or in the library or something, it's a little tougher, but if you're at home for this, I would take, especially the periodic table that I sent you, the color copy would be good, and have that out or taped up on the wall. So, I have the periodic table. I don't want to say memorized, but sort of like your phone number, you use something enough, you just know it, that you can glance over and be like, what elements are the nonmetals, and then see how many are there, etc. Okay, so the first element is always the one that's further to the left in the periodic table. The second is the one that's further to the right. And then we put an IDE on the end, usually where the root word ended in a vowel. Then we put those same prefixes in front to make it clear how many of those atoms are there. Occasionally mono is used, like carbon monoxide, but usually it isn't, because obviously there must be one of the elements there, otherwise you wouldn't be using the element's name. And these are those same prefixes, right? Mono being 1, but it's usually not used with the exception of carbon monoxide. You rarely get up to these high number ones, but di is 2, right? Tricycles, 3 wheels. Tetris is that, squared cubic video game thing, kind of old now. Pentagon is a building, in Washington, D.C., and then hexagon and on down. But we won't really use these things. It's pretty rare to have just 2 elements that make up a molecule that have this many atoms beyond. 6 is even kind of high. Usually it's 5 and lower. It's not a spelling test, and even if we have one of these naming ones, it'll be a, multiple choice. It's not going to be a spelling thing anyway. All right, so let's do an example. BF3. Go find B on the periodic table. Now this is kind of easy because it already said it's non-metals, so there's not many non-metals, so it's kind of easy to go find this one. B is boron, and then F is fluorine, so where the last vowel is, you cut that off and put IDE there. And it's easy when that element or the other element has that vowel as an I. But you kind of already know this because you breathe out carbon dioxide, so there you're already saying it. So mono boron, that's understood. You don't really need to put the 1 in, right? Carbon monoxide is the only one where the mono's actually in there. And a lot of times this happens in science and things is once something is called something like carbon monoxide, it becomes just common vernacular, and it's hard to get rid of. All right, so the first one is N, and oxygen, so nitrogen, and then we have 2 of them, so nitrogen dioxide. 2, phosphorus pentachloride. 3, that would be diiodine heptafluoride. So again, what's easier is, or the trick to this is if it's written out with the formula, then it's not too hard. But if you get to a problem that has, say, phosphorus pentachloride written out, and you don't know those prefixes, you could take the wrong formula, or you'll spend time looking it up when you could be going ahead and working out the problem, that kind of thing. And this just goes back and forth, right? From the formula to the name, from the name to the formula. Obviously, it's nitrogen. Obviously, it's oxygen. Di is 2. Penta is 5. So N2O5. Couple more. I mean, this one's pretty similar to the last, right? It's nitrogen, oxygen again. Di and tetra, so N2O4. Sulfur, and then hexafluoride. This one gets used in, actually is relevant and gets used in a lot of organic chemistry and some computer production type of things. But anyway, sulfur, and then hex is 6, so SF6. Arsenic, you maybe heard of before. It's usually has kind of a negative connotation because it does bad things biologically to biological life. But di and then tri means 2 and 3. Okay, acids. Acids are used to break bonds, and that's why our stomachs are acidic, so that when you eat food, it helps to dissolve and break these things up. They always have to have an H in the formula because they're going to produce an H when they dissolve in water. Most fruits are acidic, and you've had a lemon, a lime, I don't know, a grapefruit that got a sour taste. We haven't gotten to why, but they dissolve metals, and this is sort of a classic first Chem 161 experiment. But it depends on if you have a lab, who you're taking it with, etc. All right, then for us, it's always going to start with an H. So whenever you see a formula that starts off with an H, that should, ring in your head that it's an acid. And this is one of these typical experiments where they take a little bit of zinc, and in Chem 162, you do the math on why this happens. And the more reactive the metal is, the more bubbling that you'll see, and the bubbling is H2 gas. So the reason it says H3O plus here is you have some formula where there's the hydrogen pops off whatever it's with, in this instance, the chloride, and it just hops onto a water, and then the water sort of carries it like a chaperone or something or whatever, handoff, like the baton on a relay race, and gives it to the zinc. And the zinc, the strip of it is zinc metal, and then it goes to zinc 2 plus. But all the charges will be important in 161, not here. Same thing here, obviously, when we're still naming things. I'll probably put 1 on the exam, but again, it's when you can have things taped up or Google the name, the formula, and get the name. There's no point in putting it on an exam. Okay, the H in front, and either it's a polyatomic ion or it's just binary, which means 2 elements. And those polyatomic ions are all the oxyacids are all those polyatomic ions. When it's just 2 elements, we write hydro in front, and then ic after the name, and acid afterwards. So HCl, the acid, is then obviously chlorine. It would be chloride, but since it's an acid, ic, we put a hydro in front, and so hydrochloric acid means HCl. So again, the more of these things you know, the easier it will be to work through problems and not have to go look up names and stuff to know what chemical they're talking about. All right, the oxyacids, similar kind of thing here, right? There's the 8 and the I, and that translates to ic and us. No hydro this time, and then an acid at the end. So, right, this is sulfate. That becomes sulfuric, right? The root of the word. This one's a little different in that, the U is back in there, the UR. But it just, once things get named, it's the way it is. So no hydro and sulfuric acid. And we'll only use 5 or 6, maybe a 7th acid all year long. In the labs and, in the book, etc. So here's the same thing, but 1 less oxygen. So it's not sulfate, it's sulfite. And so that becomes sulfurous. Again, no hydro, so sulfurous acid. H2SO3 is sulfurous acid. All right, just a couple of examples. The first one you can obviously see is binary, right? And then here's one of those chlorate polyatomic ions, and then the more common one, the nitrate. So hydro, because there's 2 elements, it's sulfur, so sulfuric, and then acid. It was chlorate, now it's chloric. It was HNO3 would be the 8. This is the ite, so nitrous acid. Okay, so the names are pretty easy because you always see it ends in an acid. The formula always starts with an H. The hydro prefix telling us it's binary. They call these oxyacids because they're all those polyatomic ions. This is just sort of a summary page where, remember, the central atom had then oxygens attached to it. All right, hydro, again, so it's telling us it's binary. Sulfuric sounds just like sulfur, and acid tells us it's an acid, so we want to start the formula with an H, right? We need it to be balanced. Look where sulfur is, it's in group 2, so this looks similar to the ionic. We need it to be neutral, and then almost all these acids, unless they're in the gas phase, they're really hydrophilic or water-loving, so that you always show them written with an aqueous afterwards, right? And our charges cancel. Carbonic, this is our polyatomic ion. The H goes first. There's no hydro, which means that it's one of these polyatomics. The only one that has carbon in it is CO3 2 minus. The charges clearly don't equal each other, so we need to have twice as many hydrogens. Right now our charges are equal. It's aqueous because all these acids are, in water, and they love water. So even if you produce them on their own, there's moisture in the air. Just like, when you take something cold out of the fridge, you can see water start beating up on it. It's the same thing with these types of compounds. And our charge is equal. All right, one more. No hydro. We start with an H. This is a sulfur-based one. It's SO3 2 minus. That's the ite. We need 2 of the hydrogens again to balance the charge to be neutral. So sulfurous acid. Here we're going from the name to the formula. Before we went from the formula to the name. Okay. So once you know what the names of things are, basically our next step here is we're going to start having chemical reactions happen. And in order to have chemical reactions happen, the amounts of them have to be the same. So we've got to dive into what the mass is. So the mass of some molecule or formula unit, which is saying this generically. So a molecule would be a bunch of nonmetals that make up a molecule. Atoms that come together to make up some molecule. And formula unit is the ionic. So its formula mass is generically describing both those situations. And then depending on what book and what country people are from, you'll kind of see it written in any one of these things. You'll see molecular mass, molecular weight. They all mean the same things. And what it is it's the sum of the mass of the individual atoms. All right, so the mass of water, for example, is twice the mass of hydrogen plus the mass of 1 oxygen. That was doing AMUs if it's for one molecule, but again, we covered this with Avogadro's number. These things are really small, so we have to group a mole of them together so that we have a reasonable amount. So here's from the last slide, right? The formula mass, if it's an AMU, this would be, the mass of 1 molecule, but you can't pick up 1 molecule of water. These things are tiny, right? But you can pick up a mole. And the mole is 2 times the mass on the periodic table in grams instead of AMUs. So you can pick up a mole of water because it'd only be 18 grams. Okay, so this one doesn't have the animation, but this one's going from the mass amount to the molecules. There'll be one like this on the periodic table. Like you have to walk away from Chem 161 knowing what Avogadro's number is and use it. So there'll be one of these on the final, and there'll be one on our first midterm, but there won't be Avogadro's number on the 2 middle midterms. But grams and moles will continue to use in Chem 162, and you'll use it in OChem as well. Because you have to weigh, to do a lab, you're going to weigh out some chemical, and you need to know how many molecules or how many moles, more important, there are there, and that's based off the molar mass because you weigh it out on a scale, and the scale weighs it in grams. So this one, how many molecules are in 50 grams? Right, 50 is the unit grams that were in of lead oxide. We want to know how many molecules. Well, first, let's get out of grams. So the molar mass does that for us. Then we're in moles, but that doesn't get us to molecules. The Avogadro's number does. So moles of lead on the bottom and Avogadro's on the top. Again, this is kind of like, how many minutes are in a day. You just do 2 conversion factors. You go from days to hours and then hours to minutes. So it's the same type of dimensional analysis that you've done before in a math class or physics or whatever. It's just new units. In this one, it's moles and grams and then moles and molecules. But the concept is the same. Percent composition. So it's just like it sounds, right? You know what a percent is. Composition is what makes something up. So it's just a percent of each element in some compound, whatever it is. And how, we do this by the mass of them. Right. So first you have to know the formula of the compound, right? H2O, for example. Then you can either do this experimentally, and we'll walk through it, but I won't put one of these on the test. They're a little bit long and tedious, and they're kind of foreshadowing for OChem, but I know not everyone's taking OChem. The percentages may not always total 100. They're going to be really close, and the ones we do, they'll be awfully close. Right, and you know that the percent is whatever you're interested in over the total times 100. All right, so there will be something similar to this on the test, because this is an easy one that's hard to Google. I can make up some strange molecule that doesn't even exist, but you can still obviously do the math on it. Okay, so this is saying find the mass percent of chlorine in C2Cl4, Cl4, sorry, yeah, F2. Okay, so that's what they gave us. We want the percent of the chlorine. So we need to find how much chlorine, and they're doing it generically here with X, but it should be Cl, right? And then that's the generic one then above. So to find how much the percent is of chlorine, we need to find the mass of the chlorine over the mass of the total, right? Chlorine is the thing that we're interested in, and then the total is all the elements that are there. So from the periodic table, 35.45, chlorine, right, the formula told us there's 4 in them, and that's what's going to go on top, and then we need the mass of everything and divide it. And here we get 69.58%. Does this make sense? Yeah, so it's less than 100. Obviously, the percent has to be between 0 and 100. Carbon and fluorine are both lighter, and together 2 and 2, there's 4 of them. So there's more, the number of atoms in chlorine is the largest. The chlorine is the heaviest, so the percent should be the largest, well over 50%. So that one makes sense. On some of these, you can rationalize whether your answer is reasonable and makes sense. All right, here's another example. We're doing mass of calcium in calcium chloride. So thing we're interested in over the calcium chloride. So this is where the naming is important. Like if this had just said calcium chloride and not had the formula, you need to go and know that the formula is CaCl2, not CaCl. All right, so get the mass of the chlorine and the mass of the calcium, and you can, since there's only 2 elements, you can find one and subtract from 100, or as long as you do the first one right, or you could find them each individually, and that's what they did here, right? The mass of the chlorine, and then the mass of the calcium, and again here they did found 136.11, and then you could subtract that from 100 and vice versa. So it just depends on what it's asking for or how you want to do it. All percents are a ratio of 2 things, and a ratio of 2 things is a conversion factor, right? It's not a definition one like 24 hours in a day, but it's still a ratio of 2 things. And so in mass percent, it's telling us how much of something we're interested in versus the total or something else. So in this one, it's telling us this, carbon, Cl2, F2. The reason it's picking these things is they get used in refrigeration, and because they're an inert gas. And we'll talk more. We'll see these molecules that have carbon, chlorine, and fluorine in them again. Okay, they're saying they already did the math, the percent, and figured it out that it's a fact that it's 58.64. And then when you're doing percents, if you just assume you have 100 grams of your compound, then the percent turns directly into a gram amount, which is kind of nice. Right, because percent is out of 100, so if you assume 100 is the total, then that percent becomes just a gram amount. And then now you have a conversion factor to do whatever you want with. And vice versa, right? So here it is in a typical percent, but you know, like just like 24 hours in a day, depending on what it's asking you for. You know, if you're going up to years or down to minutes, then you'll flip-flop your conversion factor to get you wherever you want to go. Okay, you don't need to know what benzaldehyde is. This is an organic chemistry molecule. Um, we don't care what it is. The only thing missing here is, well, it just asks us what the carbon is. We don't even care what other elements are there. It's saying that it's, you know, 79.2% carbon. What mass of benzaldehyde contains 9.8 grams of carbon? Okay, so what do we know? It's giving us information on the percent and the carbon. It wants to know what mass, if we had this much carbon, what would the total be? So we know if we just assume that there's 100 grams, and that means 79.2 of it is carbon. It's giving us a carbon amount. We'll use the percent. And here again is where it's flipped because we're finding the amount of the total. So we know it's, you know, about 80%, and round this 19.8 off to 20. It's saying that the grams of the carbon is about 20. That means the benzaldehyde should be about 25. So this number seems correct, right? And again, dimensional analysis, you want your units to cancel. Okay, conversion factors and chemical formulas. Basically, what we're working on and getting up to is balancing chemical reactions, right? All these chemical formulas, they have these same ratios to them, right? We talked about this at the beginning, right? Water is H2O. If it's H2O2, that's hydrogen peroxide, right? And you've used hydrogen peroxide before. It has a very different reactivity. The formulas are similar, but they're not the same molecules. All right, so these relationships get used to convert between the amounts of the different elements. Okay, so another example here. Find the mass of hydrogen in a gallon of water. So we're going to use a lot of different conversion factors on this one, right? They made it intentionally hard because they gave us a gallon of water. A gallon is a volume, it's not a mass, right? So we obviously need to get out of the volume and first change just from the units of the volume, but then get out of the volume and into a mass, because that's what it's asking us about. All right, then once we're in the units we really want of grams, then we can get to moles. And then last, just the hydrogen instead of the H2O. So this uses lots of little conversion factors. This one's a little over the top in the number of it, but it's a good example of unit conversion. Right, so first we're in gallons. We want to go to gallons to liters. This is the wrong unit for density of grams per mil, so we want to get out of liters and into milliliters. Then this isn't much of a conversion factor, right? 1/1 is just 1. But still a couple of conversions. Okay, then at least we're in mass, but this isn't the mass of hydrogen, it's the mass of water. The molar mass or formula weight of water is 18, right? 2 hydrogens and 1 oxygen. But then it wanted the mass of hydrogen, and how many hydrogens are there in water? There's 2 for every water molecule. And then what does hydrogen weigh? It weighs 1.008 grams per mole. So again, lots of unit conversion here. You know, this would be like asking, you know, how many seconds are in a year. you need to line these up and have them get out of the units you're in and keep moving towards the units you want to be in. Now, this one here, they say check since 1 gallon weighs about 3,800 grams and hydrogen is light, the number makes sense. Well, I don't know what a gallon weighs off the top of my head. So some of these, the numbers you can get a feeling for if you're in the right ballpark or close to what the answer should be. And others, the number can be pretty big or small. You do so many conversion factors along the way. You'll have to be much better at math than I am anyway. The empirical formula, we saw this in the beginning. It's the simplest ratio. So if you remember lowest common denominator when you're adding fractions together, we did this for the empirical formula. It's pretty easy math, and there'll be one of these on the test. This elemental analysis is an OChem thing. I'm not going to put it on the test. It's called combustion analysis because literally they burn it to get these things, and that helps you find this percent composition. So we'll go through one of those in a minute, and it combines everything that we've just talked about, but it's a pretty lengthy problem to put on just as one problem. But an empirical formula one seems fair enough, and this is, slide 88 walks you through this. Convert the percentages to grams. So with all these things, percentages, if you just assume you have a 100-gram sample, then the percentages are the gram amounts. Right, then everything has a different gram amount, every element. So the different gram amounts don't really help us. We want to use the mass on a molar ratio to figure out how many of them there are. When it says write a pseudo formula, what it means is that the ratio that you get, it could be the empirical formula, or you could have some whole digit number that you multiply it by to get to. Divide the smallest number of the moles, and you will get whole digit numbers, right? This is usually for people, this was an old way of analyzing molecules a long time ago, where I'll give you numbers that come out really close to whole number. Multiply all the mole ratios by a number to make them all whole numbers. I know that's kind of wordy, but what it means is, like, if you get a half, that means you need to multiply by 2, right? 0.3333 is 1/3, so you multiply by 3, that kind of thing. Think of this as like money, right? 4 quarters and $1. If you have a half dollar, 2 of them gives you $1, that kind of thing. Okay, so let's do one here. Aspirin is something you've probably taken before, right? When you have a headache, they're saying that the percentages of carbon, hydrogen, oxygen in it are these amounts. What is the empirical formula? So if we just assume that it's a 100-gram sample, then each one of those percents becomes the gram amount. Right? We know it's CX, HY, OZ. We just don't know what X, Y, and Z are. So let's take each gram amount and change it into a mole. And you do that by off the periodic table, right? The mass off your periodic table for carbon, hydrogen, and oxygen are roughly 12.01, 1.008, and 16. All right, so if we take each of those gram amounts, we'll get the mole amounts. Now, this is where that verbiage usually gets a little confusing. So what you do is you divide these by the smallest number. The oxygen is the smallest number. Right, so 2.22 divided by itself means 1. This one, the hydrogen, was pretty easy to see that it was about, twice as much, so 2. But here we get this where it's about 2.25. So you can't have a quarter of an element. They have to be whole digit numbers. So if it's a quarter, there's 4 quarters and $1. We multiply this by 4, and that gets us to the empirical formula. So the empirical formula would be C9H8O4. So on the test, I have to make up some molecule. I'm not going to tell you it's aspirin, because then you could just Google aspirin and the Wikipedia page or whatever would have the formula. So that's for organic compounds. It's a little bit easier for these binary things or ionic compounds. This one's saying, because it's just two elements, iron and oxygen, so a bit easier. A lot of these different iron oxygen compounds have these different, a lot of times Latin and different names from when they're discovered and who they name them after, and Greek stuff. Anyway, so it gives us the percent of iron. Subtract from 100 the rest of oxygen, obviously, is the rest, so 72.4, 27.6. If we assume 100 grams, then those percent amounts become the gram amount. We change those into mole, and then usually these jump out at you, right? So let's get out of grams, and we see 1.3 to 1.73, so that looks to me something like 2 to 3 or something. You divide them both, and obviously the smaller one just becomes 1, so 1.3, so that's a third. We multiply both by 3, and we're going to get 3 to 4, right? 3 times 1 is 3, and then 3 times 0.133 is 4. So none of these are too, none of the math is too difficult on its own. It's just the format and knowing which step to take. And I know there's a lot, you're taking a lot of classes and a lot of new stuff. And so each little thing we do isn't hard, but it's the total of it that gets to be a lot of stuff. So we covered this in the beginning, right? Empirical formula means the simplest. So for example, hydrogen peroxide, H2O2, its simplest empirical is HO, right? Then you multiply it by 2. So the molecular is always some multiple of the empirical. Even if they're the same, then you're just multiplying by 1. So we went through how you find the empirical, and the molecular is just going to be some multiple of that. So if you divide the two, then you'll get that whole digit number n that you're multiplying by. Okay, this 13.18 is butadiene, some organic molecule. Again, it's not an OChem class, but most people do have to take OChem, so they throw these in here to foreshadow, because a lot of people are going to have to take OChem. This one's telling you the empirical formula, which is left out of the top part, but saying it's C2H3O. And if the molar mass is 86.03, what is the molecular formula? Well, the molecular formula is when you divide it by the empirical mass, then you get this whole digit number. So let's take the empirical formula, and it could be the same thing if this n digit is 1. So we take the mass of carbon times 2, mass of hydrogen times 3, and oxygen, right? So 2 times carbon, 3 times hydrogen, and 1 times oxygen, add them together, and we get 43, right? And again, you can already see, right, 43 times 2 is 86. So usually you get a number that jumps out at you, right? 43 is obviously not 86, but you can see that it's this nice whole digit number, right? Within rounding, of course. So then you need to multiply that formula, the empirical one, times 2. And if you knew organic chemistry, this buta here means 4 and carbons. And then the di part is an oxygen naming thing. So you'd be looking for something with 4 carbons and 2 oxygens. But obviously, you haven't had OChem yet. So here's another one. So again, an OChem molecule, you obviously don't need to know the name of, tells us the molar mass, tells us the empirical formula. Even this one, this is really similar to what a test problem will be like, where you don't really even need the periodic table. It gave you the mass right here, so everything you need to do the problem is right here. So let's find the mass of C5H3. 5 carbons, 3 hydrogens. You get that added up at 63. That's clearly not 252, but it's got to be some multiple of it. So we divide 252 by 63 and we get 4. So then we just need to go and multiply that empirical formula by 4. 4 times 5 is 20. 4 times 3 is 12. The right answer is C, 20H12. So this is a good slide 107 kind of benchmark it, come back to it maybe before the test. And this is a good example of a test type problem. And I'll have to just make up some molecule and not give the name in here, because then you could just search that. Okay, I used to put one of these on the test, but in these online tests, we have a lot to do, and it would really need to be laid out in several problems because this is long. So an in-person class, I put a couple of the naming ones in there, but the naming ones, either you know or you don't. You can't, pick up a calculator and work on it. So the in-person exams usually have a few 5 to 10 really easy problems that, only take you seconds to do. So this one, the combustion one, is a long one, and so I won't be putting one of these on the test, maybe parts of it, but to do it from scratch all the way through is a little long. And this is really old chemistry that's being phased out. So even now, if you're a chem major, they make you learn this so that you know how things used to be done. It's kind of like, I don't know, telling time by a sundial or something. No one does it anymore. Okay, so notice here a common technique. I mean, it used to be, but now we have much more high-tech ways to figure out what molecules are than, this is the old sundial. So older professors that actually had to do this stuff, for 30, 40 years ago, used to make students, maybe they still do this, but it's too much for us. And notice here, organic compounds. So this is an organic chemistry thing. So you might want to pay a little more attention to it if you're a bio major and you have to take OChem, because you'll probably have a lab where you do this in OChem, but if you're not taking OChem, you'll never do this again. Okay, so basically what they do is they take it and they burn it up. So when you burn something, all the carbon that's there comes off as CO2. Then they have a way to trap the CO2, so you can measure the CO2, which indirectly tells you how much carbon was in your molecule. Then any water or any hydrogen that's in there, when you combust it, the molecule breaks apart when it's burning and catches on fire. The hydrogen forms water. So if you can trap the water that comes off when you burn it, then you'll know how much hydrogen was there. And then the oxygen you do by subtracting. Once you know how much carbon and hydrogen is there, the rest of it is oxygen. Now, this assuming, makes the assumption that you have no other element in there. So sometimes, if you know you have other elements and you ignore the oxygen. And this is what these things look like. So, this is a simplified version of it. And you rarely do these yourself anymore. You send it out to a company that has much better high-tech things, ways of doing it than this. But you put the sample in and you burn it, and then you absorb the water in the gas phase, right? It's a gas coming off here. Then how much water is on here, that tells you the hydrogen. How much carbon's on here, that tells you the carbon, and then you can start to piece together the formula. This is important when you think you've made something and you want to convince other people that you've made it. But okay, so this example, it wouldn't be on the test as all one problem. Maybe split apart into, this would be worth like 2 or 3 problems, and it encompasses everything kind of we've done this chapter so far. Okay, it's saying we have this gram amount of a sample, and then it came off, the masses came off of carbon dioxide and water with these amounts. So this indirectly tells us the carbon, right? Not the hydrogen or not the oxygen that's on them. All right, we know that our formula is going to be CHO. We're just looking for that X, Y, and Z. It gave us information about the carbon indirectly with the CO2 and the water. So from there, we can get to the moles of CH, and that'll get us to that X and Y up there in our formula. Once you know X and Y, you can subtract it from the total and get the mass of the oxygen. Get that to the moles of the oxygen, then we can make that pseudo formula and get to the empirical formula. So you can see how this is a little bit much for one problem on the test, right? Even each arrow, like, 1, 2, 3, 4, 5, 6, 7, 8. This is a bit much for a problem on our exam. Again, I used to do it because it was easy to have a few naming ones that were so simple. You got to budget time during an exam, so there won't be one of these full problems that's worth 1 point. That'd be a bit ridiculous. All right, then here's all the relationships off the periodic table. You could start with the water or the CO2, doesn't really matter. This one, the way it's solving, they chose the CO2, so that's fine. This was the mass they said came off. Right, we know how many grams are in 1 mole, so this tells us how many moles of CO2 there were. We only care about the moles of the carbon, right? And this isn't much of a conversion factor, 1 to 1. They gave us the mass of the water. We want to figure out the moles. Now, the hydrogen that's on here that came off is from our compound, and there's 2 moles of hydrogen and water. So now we have our moles that are in our unknown compound. So if we take those moles, we can get to the gram amount. We add those together, and we know that's the carbon and the hydrogen. We subtract that amount from the total, and this indirectly gives us the amount of the oxygen. From the grams of the oxygen, off the mass on the periodic table, we can get to how many moles of oxygen. All right, now we've got all 3 values for the moles. We divide them by the smallest value. And this one worked out really easy. Obviously, the oxygen is going to be 1, but then these other 2 values came out to really close to 10 and 12. So we don't need to do any more multiplication. Oops, it's just C10H12O. So you can see, like, that has too many steps in it for one problem on the test. So there won't be, there'll be 25 questions on the test, and this one would take me, 10, 15 minutes to do. That clearly doesn't leave you time for the other problems. So this is really like 3 problems in one. This is a good one to come and do and see if you can do it, next week or 2 weeks before the exam or something. Come and see if you can do it. But don't expect, think of this as representing one of the 25 problems. That'd be difficult for me to do it. Okay, this one does the same thing, same format, so I'm not gonna walk through it as slowly, I guess you could say, as the last one. I don't think the animation matches, but it's a similar type of problem, right? The combustion tells you it's this type of problem. There's our sample, here's our water and CO2. The only difference here is now it's telling you the molar mass. So once you get to the molecular formula, so this is just multiplying by that whole digit integer. But otherwise, the process is the same, right? From the CO2, we find out how much carbon there is in moles. From the water, we find out how much hydrogen there is. To get to the oxygen, we need to subtract those two amounts from the total. So we add these two together, take the difference. Once we have the grams, we use the molar mass to get to the moles. Now we know the grams of each, the moles of each, our pseudo ratio divided by the smallest. And they come out to roughly whole digit numbers anyway. So now the only difference is this the correct formula, the empirical versus the formula? Add up those masses, we get to 58. They told us it was 116, right? Ballpark, that's about 2. So we would need to multiply the empirical by 2 to get to the molecular. Again, right, lots of steps. To me, this looks like more like 3 problems in one. You know, something like filling, like you fill in the table here. Like if this problem was on the test, it would be, you know, like filling in each of these values would be one question or something. But even still, I don't think that's fair, because, you know, if you make a mistake on one and that could propagate through the problem, then you would miss 4 points, 4 questions on the test. So that doesn't really seem fair to me either. All right, so the whole point of this for us, working through these and the formulas and the equations, is because the majority of chemistry, all semester, all year long, and in OChem too, is about chemical reactions. Especially when you get to OChem, you're going to go into the lab and you're going to take molecule A and molecule B and mix them together. So what we're really getting to is reactants and products. Right, and this is showing you, again, the guy in this book, he just must love cars, because the internal combustion engine is in a lot of these examples. And it's a good example, so rightfully so, but he just seems to be quite enthusiastic. Gasoline is what you go to the store and buy. Oxygen's in the air, right? And you burn it controlled in your car. The carbon on your gasoline comes out as CO2, the oxygen in the air combines with it. And the same thing with the water. So we have these non-oxides that burn, and out the tailpipe, where the products come, the oxides of those elements, carbon dioxide. And, you know, you could call hydrogen, water, dihydrogen monoxide or oxide, but we call it water. Okay, so chemical equations are a shorthand way of describing a chemical reaction. Just like the way when you were learning math, if you got a word problem, you pulled out the information out of a word problem. You know, Johnny has 2 apples and he gave them all to Sarah, who has 7. 2, you know, how many apples do they have together? That's 2 plus 7 equals 9, right? It's the same thing here, but it's for chemicals and chemical reactions. What does it tell us? It tells us the formula, so which chemicals are reacting and what products are being formed. In parentheses afterwards, you'll see the states. So it'll tell us if it's a solid, liquid, or gas. Relative numbers, they have to balance each other, which we'll see coming up. Then we can use these and the weights of them, of the reactants and the products, and you can figure out how much using how much reactant, how much product you'll get. And in theory, vice versa, but you know, reactants, chemical reactions are the reactants changing and going to the products. There's a forward direction to it. Okay, so for example, combustion means to burn something, and in the chemical sense, that means reacting it with oxygen and getting the oxide chemicals of the individual elements. Methane, you commonly know as natural gas. If you have a gas stove, or anywhere you've lived, if you've ever cooked with gas, right, you can hear the sparking as you turn it on, the sparker trying to light it over the stove. And then this is the gas that's flowing out. it combines with oxygen that's just in the air. Remember, oxygen is O2. It goes to make carbon dioxide and water. So if you noticed it here already, our problem here is that there's 4 hydrogens over here and there's only 2 on this side. So it's not equal, right? And then on this side, you can see we have 3 oxygens, but over here we only have 2. So that doesn't equal each other. What do we need to do? We need to do what's called balancing, right? Conservation of mass. You can't have elements showing up that weren't there to start off with. So the way we do this is by putting a coefficient in front. This number in front is called a coefficient. It's always an understood 1 that's in front of every chemical formula. So it's when we need more than 1 that you'll have this coefficient in front. And what you do is you multiply this coefficient times the subscript in the formula behind it. So still 1 methane, but now 2 oxygens, right? Still 1 CO2, but now 2 waters. So 4 times 1 here, and then, or 1 times 1 for the carbon, 4 times 1 for the hydrogen, and then 2 times 2, so 4 total oxygens. Over on the product side, the understood 1 that's there, 1 times 1 carbon, we have 1 times 2, so 2 oxygens. Now we have 2 times 1, so 4 total oxygens, and then 2 times 2 for the hydrogens. Again, the coefficient in front times the subscript in back. Right, then down here is just, counting them up and seeing that they're equal to each other. All right, so the way this reads is that methane gas is reacting with 2 moles of oxygen gas to produce 1 mole of carbon dioxide gas and 2 moles of water. And G meaning in the gas phase, so you can say 2 moles of steam. Right, those coefficients, you have to manipulate those to get the atoms to equal each other. So now that we've done that, this equation is balanced. So if you see an equation that doesn't have any coefficients in front, you want to check to make sure that it's balanced, which sometimes it is in a 1-to-1-to-1 ratio. But you want to check and make sure that it's balanced, because if it's not, you'll never get the answer correct, whatever problem you're doing. So here they're going back and just doing what we already saw, right? Count the elements on each side. So there's 1 carbon on each side, 4 hydrogens on each side, 2 oxygens. Here's what all these, all of our symbols that go in there mean, right? G is gas, L is liquid, S is solid. We kind of already knew that. This is sort of the newer one. AQ means aqueous, and in Latin, aqua is water. So it means that whatever that species is, it's in a solution of water. These next ones aren't as critical, but again, if you're going to take 162, which most are, and then more especially OChem, these symbols are giving you extra information about how the reaction's happening. So it usually means that these things are required in order to make the reaction happen, right? You need heat in order for it to happen, or you need to shine light on it, which sounds a little funny at first, but light is energy, right? You've gotten a skin burn, a sunburn before, and that's usually from light. You can get it from heat as well, but a sunburn, we call it, from light. Then these two, electrical we'll see, but shock you don't really see too much. Okay, there'll definitely be one of these on the exam. This one is a good example to come to and see if you can do it. And then as you get stuck, hit the animation and it'll move you 1 step closer. The problem that'll be on the test is going to have to be some made up one, not something that has a chemical that has a name to it. All right, this one's saying combustion and it's carbon and hydrogen. So combustion is with reacting with O2. We get the oxides of those two elements, which are CO2 and water. Let's start counting up things and see. And usually what's best to do is the carbon, right? You can obviously see that there's only one carbon and carbon dioxide. So we're going to need a 4 in here. Now, this number 4 could change if we have to do a multiplication, but it's always going to be some divisible by 4. So it's, you know what I mean by that is it's going to be 4, 8, 12, 16, something like that. So this 4 may actually change, but it's going to be at least some multiple of 4. Okay, if we look at the hydrogens, we've got 10 on this side, and we don't have 10 over here. But if we put a coefficient of 5 in front of the water, 5 times 2, that gets us to 10. So again, is it going to stay 5? We don't know for sure, but it's going to be some multiple of 5. Okay, then 4 times 2 is 8. And then 5 times 1 is 5. 5 plus 8 is 13. So that's where this 13 came from, right? Coefficient times subscript. 4 times 2 is 8. 5 times 1 is 5. That's 13. There's no way to get 13 over here because it's for O2. So the only way to do that is to multiply everything by 2, right? You can't have 13 halves, doesn't exist. So we keep the 4 and the 5, you know, this would be 6.5, right? 2 times 6 is 12. But you can't have 6.5. You can't have a half a molecule. So what we need to do is multiply this whole equation by 2. So that gives us a 2, the 13 halves, if you will, or 6.5 turns into 13, the 4 turns into 8, the 5 turns into 10. And now if we go back and check and count each one, they're all balanced. So again, in this step up here, the 4 and the 5, we knew that it was going to stay some multiple of these. And it turned out because O2 comes as a 2, and then it was an odd number of oxygen on the product side, we need to multiply the whole reaction by 2. 145. So I need to stop there. We're out of time. That's the most challenging of the balancing. You know, multiple steps. We'll see as we go in through and do a few more that they're a bit easier than that. You know, when there's only 1 or 2, when there's only 2 atoms, the less number of atoms, obviously the easier. All right, I'm just there. So yeah, we're out of time. I have to stop there. Feel free to hang out and ask questions, and we can talk about whatever, or sign off, and I'll see you on Wednesday. I hit the unmute, so if you want to ask questions, feel free to unmute and chat, and if not, see you Wednesday.
Thank you. See you Wednesday.
Sounds good.
Quick question. Hello?
Yeah.
Quick question. So when you first introduced acid and whatnot, so everybody knows that it's typically like some type of fluid, but then when you put in aqua in there, it almost seemed like there's actually more than just like a liquid type of acid. Is there actually like other forms of acid rather than like from a liquid perspective?
So yeah. So for example, like HCl, you can buy it as a gas, but its boiling point is really low. And when you buy something as a gas, you have to have it in a metal sealed container. Like, you know, when you cook a barbecue, you have to go buy the propane tank to cook, and they don't let you fill that up because it's dangerous. So they, you know, the guy at the hardware store or the gas station does it for you. So there are acids that are when you make them, if you make them with no water around, they are just a dry gas. But all acids love water so much that it's much more reasonable to just have them in water. And then even like HCl, it likes water so much, it'll stay in solution as a liquid. So usually when you buy it as a liquid. It's kind of like, and they make it really concentrated. So it's kind of like laundry soap, right? You bring the laundry soap home and it's real thick like syrup, and you only need a little bit because it's going to dilute out in the washing machine to a much huger volume.
Hmm. Okay, that makes sense now.
Yeah, so when you see this AQ, it just means that, like, you know, you have your acid. Usually for us, it'll almost always be an acid, but let's say it's some other molecule, that you put both of them in water. And like we covered concentrations and stuff, your reaction would be two solutes that are in water. The water's not doing anything, it's just providing, right? It's just providing a way for the two molecules to bump into each other, where it's not purely the liquid form of that reactant that's acting. You know, like when you wash your clothes, the water that's in there is just to get the soap molecules and the turbulence to mix it together. And when you do your wash, it doesn't really matter whether you put full load or, a light load in there. That's just how much water goes in, right? So if you only, let's say you're washing only 2 socks, like they'll come out just as clean because it's just the water's just giving a way for the soap to interact with the dirt that's in your clothes. It doesn't, the water is just, a liquid that's moving past to make things interact. The water doesn't do anything itself, right? It's the soap that does it. Because if you just wash your hands with water, it doesn't really work that well, right?
Yeah.
Yeah. So the water's like, when someone at a concert goes crowd surfing, the lead singer jumps out into the crowd. The people are the water that just shuttle the lead singer around. So the water is just shuttling the acid or the chemical around. It's not changing chemical the formula. Like the water won't change formulas in the end.
Okay. All right then, that makes more sense now. And have a good one.
Okay, cool. Bye. Megan, you there? Did you want to ask something? Maybe you're not there.